Hello everyone. Welcome back to MAC1140 pre-calculus. So let's see what we're gonna do today. So last time we stopped at section 1.2. We talked about the theory of polynomial function. So today we continue with our theory of polynomial function. Now I want you to go back to the first section when I introduced polynomial function again, and I say that the highest exponent, the value n, it could tell you the number of zero they have in that polynomial function. Okay, but we do not know anything about the characteristic of that zeros, of those zero. Those zero, it might be a real number, it could be fraction, it could be unreal number. When I say unreal, I talk about imaginary number. I talk about complex number also. But you have to remember, when we talk about a complex number, when they throw away the imaginary part, whatever you have left is a real number. Okay, and we don't know what's going on with those numbers. We don't know like they are real or unreal. We don't know anything. So the question is raised that is that imaginary number? Could it be a zero of polynomial function or not? Oh, so that question it will be answered in this section. In this section, we also talk about when two more mathematicians very famous, very popular, and we see like how they come up with theorem and how those theorem can be used in this course to solve the problem. All right, so let's get started. So this is section 3. Again, theory of polynomial function. So part 2. Okay. So first of all, let's check if imaginary number could be a zero of polynomial function or not. We can use the remainder theorem to see, okay, and see we can use the syntactic division to check if the imaginary number I'm giving you right now is the zero of the following polynomial. So example. So given polynomial fx equal x to the third power plus x plus 10. Maybe some of you will complain about the quality of the video. I'm trying to update my doc cam. We try to get to 4K. This is not 4K. It's enough for you to see. It's clear enough. However, I want to be more beautiful. So hopefully I get the package today, and let's see I can update it into 4K or not. 4K will be very good, high resolution. The video will be more. The resolution of the video will be much better. Okay, hopefully I get it today. All right. So I give you that polynomial function, and I want you to check if the value c equal to 1 plus 2i is 0 or not. See, 1 plus 2i is a complex number, right? It's a real part, and over here is an imaginary part right here. We already talked about that in the college algebra. All right, so let's start with our syntactic division. So I'll see value 1 plus 2i right here. And I'm going to do the syntactic division. Let's see what's going on. Okay, so I'm going to just go ahead and write out the coefficient of the polynomial. So it's 1, so it should be 0 because we don't have the second degree. Then we have 1 again. Then we have 10 as the constant term. Right? No, I think I set up a little bit wrong, so it should be like this. Okay, so I drop 1 down, right? Drop 1 down. So 1 plus 2i times 1 plus 2i times 1 is 1 plus 2i. So add them up, so it will be 1 plus 2i. 1 plus 2i times 1 plus 2i. If you do on the side, 1 plus 2i times 1 plus 2i, it will be 1 plus 2i squared, right? When you start following, it will be 1 plus 4i plus 2i squared, which is 1 plus 4i plus 4 I squared negative 1, so we will negative 3 plus 4i, right? So this will be negative 3 plus 4i, and you add them up, so give me negative 2 plus 4i, and you keep multiplying 1 plus 4i, 1 plus 2i times negative 2 plus 4i, so I plot it. So negative 2 plus 4i minus 4i plus 3i squared, right? So you negative 2, 4i minus 4i, so I squared will be negative 1. Negative 1 times is negative 8, so which is give you negative 10. So add them up, you 0, and look at that. The remainder of zeros, according to remainder theorem, we have f of 1 plus 2i equals 0. It means what? It means that 1 plus 2i is actually a 0 of polynomial function. So it could be. So the answer is yes. Imaginary number, it might be one of the 0 of polynomial function. Okay, you cannot grab because you cannot see that on the graph because imaginary number is in the 4 dimension. We cannot draw that in the 3 dimension x, y, z. Okay, but it really is a 0. It's easy actually. When you had like algebra course with me, when the first time I introduced imaginary number, I kind of draw the 4th dimension for you for students to be able to see. But in this case, that's all right. You don't have to draw the intersection between the complex number and the graph. You don't have to. Okay, so, but you just need to know that the complex 0 or the unreal 0, it might be unreal number, it might be the 0 of the real function. Okay. In a college algebra, you also learn that every complex number they have the imaginary part and real part. They also have something called the conjugate. Okay, so if we have 1 plus 2, in this case, we know that it's a 0 polynomial function. The question is that the conjugate of this, which is 1 minus 2i, is the 0 or not? All right, the answer will be obtained after you learn something called the conjugate 0 theorem. So on the first Roman, I introduce you to conjugate 0. And this theorem states that if a plus bi is 0, a polynomial function, so is a minus bi, which is the conjugate of a plus bi. Okay, so if you have 3i is a 0, that means negative 3i is 0. Okay, if you have 1 plus 2i is 0, then 1 minus 2i is also 0. Okay, very easy. Okay, again, we don't have to go through the proof, but we can prove it. I mean, you don't have to just prepare for this course. For the mention, you have to someone who want to do a higher advanced math, then you have to take a course called something called complex variable, complex analysis. Then they show you how to do this. Okay. All right. Now let's jump to the example. Find a cubic function which is a polynomial of third degree with 0 3 2 plus 9 and given t to the form. Okay. 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 So this is a cubic function, and the cubic function, it's a third degree. Okay, and we have 0, 3, and 2 plus I. So if we have 2 plus I as 0, then 2 minus I is also as 0, right? Okay, so according to our factor form of polynomial function, our factor form can be written as a x minus x1, right? X minus x2 and x minus x3. Because we have totally we have 3, 0, and in this question they never mention anything about a multiplicity. So we assume the multiplicity of degree is 1, 1, 1. So this is a factor form of polynomial function. We talked about in the previous video. Okay. So x1 is the plus 0. Some student love z1, z2, z3. It doesn't matter. Okay. So I can write p of x equal to a x minus 3, right? Then x minus 2 plus I, and x minus 2 minus. Okay. So we don't, over here, what we don't know is the a value, but the a value can be found by using the function p2 equal 4. What we're gonna do, we can find that later. Right now, at this moment, we just go ahead and simplify. So we're gonna have over here to be x minus 2 minus I, and over here x minus 2 plus I. Right? So what we have? So we're gonna start falling the imaginary number together. I start falling. So what we have? So I'm gonna let you do the falling part. So I'm just going to write out the solution. So we're gonna have something like this. Okay. Okay, and I start expanding. So we're gonna have x squared minus 4x plus 4, I squared equal to -1, negative plus 1. So we're gonna have ax minus 3 x squared, okay, minus 4x plus 5. There you go. And let's see, unless we can factor this or not. No, we cannot. We can't. So we just leave that. Well, it's understandable because we usually, originally we have 0 as the complex number. We cannot factor this. All right. So our job right now is to get a value, because we almost get the function already, except for the a value. The a value is the leading coefficient, so we need to find a value. So we see here the input is 2, output is 4. So output is 4. I'm going to put over here as the px. A input is 2 minus 3. So 2 squared minus 4 times 2 plus 5, which is negative 1a, right? Over here, a squared is 4 minus 8 plus 5, so which is 4 equal to negative 8 times negative 4 plus 5 is 1. So your a should be negative 4. Okay, hopefully I don't have any careless mistake. You guys can go ahead and back and check for me, but I don't think so. So your a is negative 4, then our final answer would be p of x equal to negative 4x minus 3, x squared minus 4x plus 5. This is our final answer, and this is the cubic function we looking for. Some student they want to distribute it, that's fine, that's even better, but you can leave it in factor form like this. Okay, you don't put it over here, you don't put in this one because it's still in complex, so you need to change everything into variable x. Okay, no I. Okay, so you gotta use this. All right, not this one, not the second one. this one. All right. So that is the well, that's an example. So you see that the complex number, the unreal zero, could be the unreal number could be a zero of a polynomial function. Okay. But the question, there's another question there is that a polynomial function is always have a complex zero, or it always have a real zero or unreal zero. How do we know that? A very great mathematician, German one, named Carl Friedrich Gauss. Gauss is very talented. He's a very intelligent guy. He's a child prodigy. And, he come up with this theorem, the one I'm talking about right now, when he was 22 years old. Okay, you can look it up information about him on the internet. Gauss is like a genius. So he come up with a theorem called a fundamental theorem of algebra. So let's have a part. So I'm going to talk about fundamental. It's too prime, right? Theorem of algebra. And the theorem states that every function defined by a polynomial, I mean every polynomial function of degree greater than 1 or more, greater than 1 or more, has at least one complex zero. Okay, so it would be never, it would be no solution. It would be never no solution. Okay, so it can be no solution. If the degree is greater than 1, it always have solution. Okay, it depends on what type of solution you talk about, a real solution or unreal solution. Over here, Gauss mentioned complex solution. Okay, yeah. When he means complex solution, he means real and unreal at the same time. Because remember, if you have 1 plus 2i and you throw away the imaginary part, number 1, that is the real part, is still considered as the complex zero. Okay, so when he means complex zero, he means that it includes real one and unreal one. All right, so remember that. So at least one complex has at least one complex zero. It means that if you have the degree, the highest degree is n, okay, it means that at most they have it might have, so I'm going to put over here, it might have at most n complex zero. You might be able to find few of real zero, and the rest of them will be unreal one. For example, the fifth degree, right? I just give you an example, okay? And you find out that you can find only 2 real zero. Okay, it means that you possibly you may have the 3 more left. Okay, at most 3 more left, right? And 3 more must be the unreal one. So totally we have unreal is 3 0 and real is 2. So totally we have 5 0. When Gauss talk about the complex zero, we talk about the totality of unreal and real. All right. All right. Let's go through the example. Let's go through the example. Something like this. Example 1. Find all complex zero of fx equal to x to the 4 minus 7x to the 3rd plus 18x squared minus 22x plus 12, given that 2, 3 is 0. Okay. So how are we gonna do this? Remember the n over here is 4. N over here is 4. And over the question they also say that 2 and 3 is 0. So there are 2 more 0. And 2 and 3 is real 0. So there are 2 more 0. And those 2 more 0, we don't know. According to fundamental, there are 2 more 0. But we don't know is those 2 more 0 over there is real or unreal. All right, so we had to find out. After we find out, and you will see that all the 0 you find out, you satisfy the question, right? Because they ask you to find all complex 0. Actually, most of the question they ask you to find all 0. When they say something to find all 0, you have to find the unreal one and the real one. Okay, but because we're learning fundamental theorem as well, because Gauss mentioned the word complex 0, so it means it's real and unreal at the same time. All right, so we have 2 real already, and we want to check that the rest of them will be real or unreal. Okay, and there are 2 more. Okay, there are 2 more. It might be repeated, but I don't think so. Let's do let me use the syntactic division. You can use syntactic division to check the remainder theorem. The theorem to check if the order, do we have any order 0 or not? Okay. So according to fundamental theorem of algebra, we have at most 4 0. Here we have 2 already. So let's do the quick revision. So let's start with number 2 right here. So I have 4, negative 7, 18, negative 22, and 12. Okay. So up and down. 2, negative 5, negative 10, 8, 16. Is negative 6, negative 12, negative 0. Here you go. So the 2 is 0. Okay, satisfied. Okay, makes sense. So what you have left, because this is 4 degree divided by the first degree, so 4 degree divided by x minus 2, the first degree. So what you have left, the quotient will be x to the 3rd minus 5x squared plus 8x minus 6. That's the quotient, polynomial. And we keep dividing that quotient by 3. So I'm going to set up another syntactic equation for that. 1, 5, 8, 6. Okay, and up and down. 3, 2, 6, 2, 6, 0. There you go. So 3 is really a 0, 1, and we had a 30 degree divided by the first degree. So the quotient. So this I put quotient 1. This is the quotient number 2. Over here will be the second degree parabola. So x squared minus 2x plus 2. All right. X squared minus 2x plus 2. This is quadratic. In order to find the 0 of this, it's very easy. You just need to factor it. If you can factor, then you get a 0, or you can do a quadratic formula. Look like we cannot do factoring, right? Because there's no way we can do factoring. So we can do quadratic formula. Let's see. Very easy. So in order to do quadratic formula, everybody knows how to. negative b, right? So 2 plus minus b squared minus 4ac over 2a. So 2 plus minus give you 4 minus 8 over 2, which is 2 plus minus square root negative 4 over 2. It's 2 plus minus 4i square over 2. Square root of I square is I square root of 4 2. So 2 plus minus 2i over 2, which is 1 plus minus I. Here you go. 1 plus minus I is the zero of polynomial functions. So totally, how many we have? We have 1, 2, 3, 4. It satisfies the fundamental theorem of algebra because at most we will have 4, 0 total. All right. So what is all about syntactic division? If you guys know syntactic division, you know the Mendel theorem and the factor theorem. You just memorize all theorem your brain, you know, and you can apply it. All right. Example number 2. In this example, I want you to find polynomial function qx of degree 4. Okay. And with 0, negative 2, 0, where negative 2 is 0 of multiplicity of multiplicity 3. Answer. The section is a long one, so I mean, yeah, just bear with me, okay? Probably another 45 minutes. I'll try to give you more examples for you to understand. So we have degree 4. Okay. We have 2, 0. So we mean at most we have 4, 0. Okay, but we have 0, negative 2 as multiplicity 3. It means that it counted as 3, 0 already, and there's another 0 over here. It's counted at another 0, so totally we have 4. So it makes sense. All right, I want you to remember that every time I ask you to set up a polynomial function or find polynomial function of a certain degree, I recommend that you should use the factoring form. Okay, you should use the factoring form. So a over here, right? X minus x1 and x minus x2. Over here, you see negative 2 is negative 2 over here multiplicity 3 already. So over here should be multiplicity 3. And the 0, which is x2 over here, multiplicity should be 1 because they never mentioned it. If they never mentioned, then multiplicity should be 1. So we're going to have a equal x plus 2, right? Because the plus 0 is x1. X1 is negative 2. So negative becomes positive plus raised to the third power. Minus x minus the second 0 to be 0. So x minus 0. So we're going to have ax times x plus 2 raised to the third power. Okay. So our concern right here is that we need to find the a value. So you see that they don't give you, for example, in the last example, they give you the input and output so that you can find a value over here. They don't give you. So if they don't give you, you just assume a equal. Okay, so you have polynomial qx equal x times x plus 2 raised to, and that's it. You can go ahead and plot it. They expand it and point the x forward to that expansion, then you get the 40. Remember, if they don't give you the input and output, you assume the leading coefficient one. All right. Example number 3. Again, by polynomial function px. Now with degree 5. And we have 0, I, 2, -1, where -1 is 0 of multiplicity 2. Also given, this given information will help you to find a value, the data coefficient. So answer. Again, very easy. We have according to fundamental theorem algebra, we have n equal 5, mean you have totally 5, 0. It probably repeated. For example, over here, multiplicity 2 will tell you the repetition of the 0, -1. So you can start with p of x equal to a. Okay. So if 0 is I, then negative I is 0 according to conjugate theorem, right? If I is 0, then negative I is also 0. So you have x minus I, x plus I, right? Then you have x minus 2. Then you have x plus 1 because I'm doing negative. So we have multiplicity 2, everything like this. All right. And we don't want to see any I, so we are going to start falling. So I can do x squared plus 1, right? Start falling. X minus 2, x plus 1 square. And you see that it makes sense. It will degree 5, right? So over here 2, 1, 2, so totally 5. Now our job is to find a value. And if you p1 equal 2, so p1 equal 2, so px will be 2a 1 square plus 1 plus 1 into the x, so 1 minus 2, 1 plus 1 square is 2. With you a times 2 times -1 times 4, right? 1 plus 1 is 2, 2 squared is 4, so 4 times 2, 8, 8 times -2, -8, -8a. So your a should be -1 over 4. Because consume a equal -1 over 4, I can write down our final answer will be px equal to -1 over 4, x squared plus 1, x minus 2. We don't want to write with the imaginary number, okay, so we have to fix. So x plus 1. Okay. So this is the difference between the example 2 and example 3 is that in example 3, they give you input and output so that you can find a value. If they don't give you, you assume a equal 1. All right. So you see, fundamental theorem of the algebra will tell you how many number of zero totally you may have, or at most you have, include real and unreal one. However, we cannot detect which one, how many real one, or how many real one can be detected, or how many unreal one, unless we do synthetic division, right? If we look at the problem, we cannot tell. So there's a way we can identify how many real one, and we can identify which one is the real zero by a theorem. By a theorem, we call that rational zero theorem. This theorem was brought up by a French mathematician named René Descartes. So Descartes tell you that the leading coefficient and the last number, the constant term, had a relation together by set up the proportion, by set up the ratio between those numbers. You probably can find all the real zero of any polynomial function. Okay, so on the third Roman, lecture today. I want to talk about rational zero theorem. You see, actually, the name of the theorem will tell you everything. Rational theorem. Rational. It's not irrational. It's not complex. It's not unreal. Rational is real. Okay, it's in fractional form. It's real now. Okay. All right. And the theorem. Let me see. I need to state the theorem for you or not. Let me see. Actually, I can state the theorem for you, but I guess we don't have to. We just I think I should just go ahead and state the theorem for you in case. Because just some of you want to learn carefully, so just go ahead and state the theorem. I mean, I can jump directly into the example. I think just go ahead and state the theorem. That's much better. All right. Rational zero theorem. Okay, so I'll try to find the exact theorem for that. Actually, when you understand it already, you don't have to memorize the theorem at all. Not at all. I mean, you just understand the theorem. You don't have to memorize it. When I say memorization, I say it means that you really understand that, and you can state the theorem in your own way as long as it's logical. All right. And the theorem states that if we have f of x polynomial function h n x n plus a n minus n, this is full standard form, plus a1 x plus a0, and all of this has integer coefficient. Okay, has integer course, right? Okay, and a sub n must be different from 0. If a sub n is equal to 0, it doesn't work. Okay, then we can set up the ratio a sub 0 over a sub n in the lowest term. It means it's in the simplified form of that ratio, of that fraction. Okay. Then the number let me see how I'm going to state it in a very easy way for you to understand. Then this ratio, the a sub 0 over a sub n here, we can, from this ratio, we can get all the zero of this polynomial function. Okay, so we're gonna set up, so because a0 and an is in the lowest term already, right? We want to find the factor, or the factor of 0. Okay, so 0 will be the ratio between all factor of a0 and all factor of a sub n. All right, just put it that way. Okay, just put it that way. I think this is the best way for you to understand. Already, even I put it this way, because so look at it, read that, and was like, oh, what's going on? So anyway, it's not really that bad. Just go through the previous example, you know right away. The question is find all possible zero of 4x to the 4 or 3x to the 4, sorry, minus 2x to the 3rd minus x squared minus 12x minus 4. All right, answer. So how are we gonna do it? They ask you to find all the possible root. All include the complex, include the imaginary zero, the in real one and real one. You know, but according to rational zero theorem, we just can't find the real, the rational one. Okay, so let's see, we can apply that theorem to find all the real one first, or maybe this polynomial function has only real one, the rational one. Okay, they probably don't have a complex. Okay, all right. But let's find all the real one, but the rational zero first. Okay, so we know over here a sub n is 3. It's in the simplest form or not. We have to check. Okay, a sub 0 is 4. So if we set up the ratio, right? We set up the ratio 3 over 4, right? 4 over 3. I'm sorry, 4 over 3. A sub 0. A0 go first, which is the last term. It should be minus. We can put minus, but it's not really a big problem. So 4 over 3 is the simplest form already. Okay, so we don't have to simplify anything else. Now, next step is we need to find the factor of 4. So the factor of 4 is plus minus 1, right? The negative 1 is also the factor of 4. Plus minus 2, plus minus 4, right? What is factor of 4? Is the value that go into 4 evenly. Okay, it means that's the factor of 4. Factor of 3, it means all the number going to 3 evenly. So factor of 3, let's set up ratio. Okay, factor of 3 with plus minus 1 and plus minus 3 only. Right? 3 going to 3, minus 3 going to 3, then 1 going to 3, positive 1 also going to 3. Now, so the zero of the ratio between all the fraction of ratio, so 0 will, I think I messed up. So 0 will be, I'm gonna put might be, because even we can set up this ratio, we don't know which one over here is the real one. It's just the possible one. Okay, so the 0 might be the ratio between the factor of a0 and the factor of a0n. So it could be like that. It could be, so I'm going to set up the ratio. Okay, it could be plus minus 1. I set up this over this, and I set up this over this. So it could be plus minus 1 over 3. It could be plus minus 2. It could be plus minus 2 over 3. It could be plus minus 4. It could be plus minus 4 over 3. So how many possible real zero we may have over here? Totally we have 12. But we don't know which one is the one. It just gives you the possible one. But we don't know which one. Probably over here, there are 4 of them. Or maybe there are only 2 real zero. Or there are 4 real zero. Or maybe there's only 1 real zero. And the rest is complex. We don't know. Okay, but the rational zero theorem, I'm sorry for the mess up over here. The rational zero theorem will tell you the possible number of zero, of rational zero, of real one. I'm not talking about the unreal. Okay, I'm not talking about the one with I letter, imaginary part. Okay. But they cannot tell you out of this number here which one is zero. We have to check. Okay, we have to check. So how we check? Because the question answers to find which one, so we have to check. We're gonna do syntactic division. Okay, we're gonna do syntactic division. Okay, that will be take a lot of time. I take a lot of time because we had to do syntactic revision for many zero possible rational zero here. But just do syntactic revision, and the portion it will lead you to something else. You know, it will lead you to something else, and maybe from there you can find more zero. All right. Well, this is a long video, I'm sorry, guys. So we have to do. All right, so let's pick with positive one first. Let's say, okay, let's do syntactic revision for positive. So one syntactic revision. So you have 3, -2, -1, -12, -4. Up and down, 3, 1, 3, -1, -1, 0, 0, -12. Did you mess up anything with that? -1 is that -12? So look like -2 here. Add them up, you negative. So f of 1 is -8. It means what? It means 1 is not 0, according to remainder theorem. Okay. So 1 is not 0. It means x minus 1 is not a factor because it's not 0 here. All right. So maybe we try something else. Let's try. I'm going to try with the whole number first. So let's do 2. Let's do 2. What happened here? 3, -2, -1, -12, -4, 3, 6, -4. So +4, 8, -7, -14. Add them up. Let me see, I mess up again. Drop it down, 6, 4, 8, -7, -14. Add them up, give you -28. Oh, hold on. Let me see. I think I messed up because we supposed to add, right? So it's not gonna. So add -16 over here. I'm sorry. So I'm sorry. It's -16. It doesn't work. Okay, and this one you add them up. You -28. Oh, it doesn't work either. So 2 times -20 is 26, 56. So we see that it's not working. So 2 is not a 0. 2 is not a 0 either. Let me see. So this because according to what I read over here, 2 should be a 0. So I think I messed up with the number. Let me check now. So it's this negative. Question is 3. Maybe I wrote that question wrong. -2, -1, -12, and -4. So you guys good. So 2 is not. 2 is not. How about 1/3? What happened to 1/3? Let's see. Let's try to do 1/3. Let's see. So 1/3. So we have 3, -2, -1, -12, -4. Okay. So we drop it down. 3. 1/3 times 3 is 1. Add them up. -1. 1/3 times -1 is -1/3. Add them up. -1 plus -1/3 is -4/3. 1/3 times -4/3 is negative negative 4 over 9. Something is not right over here. I think I had careless mistake. I couldn't find it. Add them up. So negative 12 plus negative 4 over 9. So 12 plus 4 over 9. Let's see. So 112 over 9. It's weird. None of them is the correct one. I'm wondering if I mess up something. It should be. So one of them should be the correct one already. Let me check really quick. Some careless mistake. I couldn't find it. Wait, go back and check for me, okay? Because I think I had careless mistake and I couldn't find where it is. Something happened to me. I couldn't find where it is. It should be very simple. It's 4x to the 4. I don't know where to get this problem from. It should work according to what I buy every day. It should work. So maybe over here divided by 2. Divided by 2. I think I messed up something here. 3 negative 2. 1 negative 12. I think I messed up with the sign. You know when I wrote down the question. I think I messed up with the sign right here. That's why I try to find the question again. But I couldn't find it anywhere. So let me see. I think I wrote down the question wrong. Maybe in the text. Sorry, guys. You know, sometimes we just need to mess up one of the coefficient, then you know we wrote it out wrong, then everything wrong. You know. Let me see. Must be somewhere. Maybe this equation I just got it from internet, and it's not in the textbook. That's why it does not work at all. Interesting. So over here a0 is 4. Okay, so let me see. 4. I'm gonna do this really quick over here. X. Yeah, I know, right? Sometimes we just wrote down wrong and everything wrong. Let's do the 4 minus 2x to the third minus x squared minus 12x. Okay, minus 4. Let's see what happened. I think I have a region. I mean, actually, let's see about that. Value 0. Oh, negative 1 over 3 is the answer. Okay. So okay, I think okay, so 1/3 is not. So 1/3 over here, you see that it cannot. It's if you multiply 1/3 by 1, it's give you something. So it cannot be 0 right here. Okay. Uh, uh, let me see. 2. It said 2. 2 is 0. So maybe I do wrong division here. 2, what about 2 times 2 is 6. Add them up, you get 4. 2 times 4 is 8. Add them up, you get maybe. Oh, oh my God. Right here, I saw that. I saw that. So 7. So 28. Oh yeah. Okay, so give you some over here 16. 2 times 7 is 14, right? So 14 is going to be 2. Oh, let me redo it. Let me redo this. So 2 divided by 3, -2, -1, -12, -4. Okay, so it is 3, 2 times 6, 4, 2 times 4, 8, 7, 2 times 7 is 14. That should be 2, 2 times 2, 4. Here you go. So I end up with you 0. There you go. So 2 is the 0. 2 is the 0. All right. So let's say. So 2 is 0. It means that the portion will be 3x because the original one is 4 degrees. So you divide the first one, so the portion will be the 3rd degree. All right, the 3rd degree. So we're gonna use this quotient right here, and we keep doing division, syntactic division for it's not for the value 1 because we already did it. The work it's not for 1/3. It's not working either. We try to do for something else. So you just go ahead and try to do for because 1/3 does work. I don't think -1 work over here. So I'm going to try to do for -1/3. Let's see what happens. Okay, so we have one real 0 already. So we're gonna find 3 more. Okay, so we have 3, -2, -1, -12. Okay, and -4. Up and down 3. So -1 here. Add them up, -3. So +1. 0, 0. -12. So 4, 0. There you go. So -1/3, -1/3, it negative f of -1/3 is 0. So -1/3 is 0 of the polynomial. 2 is the 0. So you have 2 already, right? And now the quotient will be 3x squared minus 3x. This is the 3rd degree by the 1st degree, so should give you it should be 3x squared minus 3x. This is weird because I have so the 3rd degree divide by the 1st degree, so you use 2nd degree, so you -12. Okay, right. Let's check one more time. So you have 3. Yeah, so I think I messed up again. I'm sorry, guys. It's very easy to mess up. So I'm gonna use this instead of using the original one. I'm using this. It's better. So -1/3 divided by 3, 4, 7, 2. I mean, if I use the original one, it still works. But you see that this is the 4 degree, so which is divided by give you the 3rd degree again. We don't want it. We don't want it. It's we just can prove it. It's negative 1/3 is the 0, but we don't want to get the 3rd degree again. Okay, so I'm going to use the 3rd degree to divide the first so that you can get the 2nd degree. Okay. I'm sorry. So over here give you 3, right? So -1 and about 3, -1, right? You still 6, -2, 0. There you go. You see that? It's much easier. Then you will have the second portion will be 3x squared plus 3x plus 6. Okay, and you see this is quadratic, and you see if we can factor this or not. X squared plus x plus 2, you can, right? So over here, if you use a quadratic formula, it gives you 2 unreal ones. 2 unreal ones. So you have 2 unreal and you have 2 real. This one and this one. Right here and right here. So totally make it 4, right? Totally make it a 4. But and they ask you find all the possible 0. It means that you have to state all the 0. So all the 0 over here is negative 1/3, 2, and 2 unreal 1. 2 unreal. I want you to go ahead and find it yourself. But if they ask you to find only the real 0, then the answer is just negative 1/3 and 2. All right. So I'm sorry for this. Sorry for this. It's correct, but we don't need it. Okay, this one I had careless mistake, so I'm sorry. I just redo it. All right, so because they are totally the possible number of real 0 over here is 12. Okay, and it takes time for you to check. It takes time for you to check. Okay, just think about it. You had to check like all of them using tentative division. So this is the way I do it. This is the method. It's kind of tricky way, you know. I show student. So just go ahead and plug every number in one by one into the original polynomial function. Which one gives you 0? Then that will be 0. And you know that, then you start the syntactic division. Okay, so when you show me the work, you have to show me the syntactic division. But when you plug it into it to get the 0, you have to see, then you know right away which one syntactic division is working. Okay, because otherwise you have to do all syntactic division. All right. So okay, so the rational zero theorem will tell you the possible number of real 0 you might have. Decartes also come up with another rules. They tell you the possible real, unreal, and the possible of the complex one. When I talk about complex, I mean the possible of unreal, imaginary 0. Okay, by counting the chain inside, or I would call that a variation inside in polynomial function. Okay, and in order to do that, we have to evaluate. We also have to evaluate function, the polynomial function at negative x value and positive x value, because when you evaluate the negative x value, it gives you the possible negative real 0. Okay, back in the rational zero theorem, they don't tell you anything about positive and negative. But the Decartes rule side, it tells you about the imaginary one, the complex one, the real one, the unreal one, the negative or positive possible you might have. Okay, so in the fourth part of this lecture, we talk about the Decartes rule side, and we need to evaluate px and p of negative x. Okay, so we're gonna count the number of side chains in px and p negative. Okay, the number of side chain in px will be the number of positive real zero, but the px of negative x is give you the number of negative real zero. All right, let's go through an example. It's very easy for you to understand. I mean, when I say, sometimes it's a little bit confusing because I kind of relate everything together. And right now, at this moment, it's kind of hard for you to relate everything together. But I mean, when you go through the example, you will be understanding that easily. Okay, so I give you the function like this. Polynomial function 3x to the 6 plus 4x to the 5th plus 3x to the 3rd minus x minus 4. Okay, and I want you to find the possible positive real zero, the possible negative real zero, and the possible all the complex one, the imaginary one. Okay, but first of all, we're gonna count the chains of sign. Okay, so of px. Okay, so this is positive go to positive, it's not changing. From positive to positive, it's not changing. But from positive to negative, it's changing. So it gives you one positive zero. Okay. Okay. And now, if we do p of negative x, it gives you 3 negative x to the 6th, right? Plus 4. Plus 4 negative x to the 5th plus 3 negative x to the 3rd minus x minus 3. So give you 3x to the 6th minus 4x to the 5th minus 3x to the 3rd plus x minus 3. So how many times it changes? So one time, right? 2 times. Okay. So this one, they give you negative real zero. So it's possible we may have 2 negative real zero. Okay, 2 negative real zero. Okay. Okay. All right. So I want you to be careful over here. You have to subtract it by 2. Okay. Over here, you have 2 negative real zero, or you may have non-negative real zero. So you have to subtract by 2. Every time you calculate the positive real zero or negative real zero, you have to subtract it by 2 in order to get the possible value. Okay, so over here, the reason I did not subtract it by 2 because we know, we guarantee 100% this is one positive zero. Okay, but if you subtract it by 2, you see that if you subtract it by 2, it doesn't work, right? 1 minus 2, no, it's not working. Okay, so we don't have any other case of possible positive real zero anymore. But this one, we have another case. We don't have any real zero. Okay, now let's count it. So totally, our value over here, the n is equal to 6, right? So the total, we have 6 possible zero, complex zero, according to fundamental theorem of zero algebra. Okay, but for the positive one, we are guaranteed that we have one real. But for negative, we have probably we probably have 2 negative or nothing. Okay, oh, for the negative. And now for the complex one. What do you mean complex when talk about imaginary one? So we may have what? 1, 2 is 3 already, right? We have 1 positive and 2 negative, but totally we have 6. So it means over here we have oh, we missed something. Oh, I'm sorry. So over here there's another way of changing right here. So 3, 2, -1, there's another one. So right here. So totally we have 3 negative, 3 change of sign, 3 times the sign changing. So we have 3 negative 0, and you subtract by 2, so you have 1. Okay, so you have 3 and 1 right here. All right. So totally we have 6 0, but right now we have 1 positive real 0, 3 possible negative real 0. So totally we will have 4, right? And what total we have 6. So we have 2 complex, 2 unreal, 2 unreal. Okay, 2 unreal. The same thing over here. We have 1 positive already. We have 1 negative. I'm sorry, 1 negative. We have 1 negative. So totally 6, right? So we might have 5 unreal. Okay. All right. So you just need to count the number of side chains. Then you subtract it by 2. Okay. I mean, kind of a little bit confusing, I believe. So let me see. I can give you an example. Let me see. How about this? I can find something. Okay, how about this? Okay, let's do this. Example 1, example 2. We have function like this: px equal x to the 5th minus 3x to the 4th plus 2x squared plus x. So total is 5. But how many possible positive real 0? Okay, it depends on the number of side chain of px. So anything change, so 1 time, right? 2 times. So for positive real 0, we possibly have 1, 2 positive real 0 or nothing, right? Because you subtract by 2. So 2 minus 2, nothing. That's why we don't have anything. For negative, okay, in order to calculate the negative real 0, you have to do p of negative x, so negative x raised to the 5th minus 3 negative x raised to the 4th plus 2 negative x raised to the 2nd minus negative x minus 1 negative x to the 5th negative 3x to the 4th plus 2x minus x minus 1. So how many times it changes? 1 time. So the negative real 0 will be 1 negative real 0, because there's only 1 time is side chain. Okay. 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 Now, so but the total we have 5. Okay. And now you have 2 or nothing, and now you have only 1, right? 1 time 1 negative real 0. Okay. is it one time changing? Let's see, 1, 2, 1, 2. Yes. Plus x. All right. So how many unreal one? It's easy, pal. So totally we have 5, right? And you have for the positive, we have 2 are nothing. Okay, 2 are nothing. For negative, we have guarantee. We got 1 negative real 0. Then the unreal will be 2 plus 3, so you have 2, right? Nothing. Or 2 or 5. 2 or 5. All right. All right, so that's the way. This is not really big. The reason you got 2 because 2 plus 1 3. So but the total is 5, so you have 2, right? Over here 0. Then the possible of unreal must be 5. Okay. And let me check one more time if I mess up any counting. So this is 2 negative. So this is only one time the sign change. 1 or 2. 1. Oh, there are 2 times. Sorry. See, 2 times. So it will be 2. 2 will be 2. I'm sorry. 2 or 0 or nothing. 2 or 0. So 2 0. Maybe how many times is it? 1, 2. Yeah. So 2 2. Okay. So it will be a little bit change it over here. 1 and 5. Okay. 2 or no negative. I'm gonna just write like that. No negative. Same thing over here. How many times changing over here? We have 1, 2. I think there. So it's positive. So there's 3 times changing. See that I had careless mistake. So it will be 3. Okay, I'm sorry. So there's 3. You subtract by 2. So you have 3 or 1 positive. Okay. So over here you have 3 or 1. All right. So totally we will have unreal will be no unreal or 4. All right. Okay. Let me create this table again. So we have 5 here. So we have 3 times the side change on right? 1, 2, 3. So we have 3 positive with 0. Subtract by 2 or 1 positive with 0. For negative, we have 2 times change. So we have 2 negative real 0. Subtract by 2 or nothing, right? Or no negative 0. And you have 3 and 2, 5. So it's the unreal one must be. So we have no unreal 1 or we may have 4 unreal. Okay. Yep. It's very easy to make careless mistake, and I had careless mistake over there. I'm sorry for that. But it's not, you see, it's not really that bad. You just count it, but make sure you count it right. Okay, you count it wrong, everything will be wrong. Okay, so we can calculate, we can find the number of unreal and the number of positive and the number of negative real 0. The thing is that I mean, for the polynomial function that has the low n, I mean, for the 4, 5, 6 degree, you know, you can do syntactic division easily in order to say which one is 0 or polynomial function. However, what if we have the degree that's really high? So in that case, in order to find the 0 of that polynomial function, it's to be very tough. And I mean, you see that when you plug into calculator, it always can find a zero for you no matter what you read. Okay, actually, calculator use a theorem. We call that boundedness theorem. Okay, so in the next part of the lecture, we'll talk about boundedness. Can restrict the boundary of number of zero. Help you, even though if, for example, if you have a polynomial n400, you're not gonna sit down, do some examples for all possible, or you can set up the rational zero and no, right? You're not gonna do that because it's too many. So the boundedness theorem, actually, it based on the Cauchy theorem. Cauchy is a French mathematician. Okay, it's based on one of theorem by Cauchy, and this theorem can help you restrict the number possible. It might give it. This theorem give you the upper bound and the lower bound of the possible here. Okay, if we can show that a number is zero of a polynomial function, and we can show that that number is the upper bound, then all the value in the rational number of zero, okay, you might have that's greater than the boundedness, the upper bound zero, it won't be zero. Okay, so it's kind of very hard for you to imagine. Okay, let's go back to the rational real zero. I don't know. Well, okay, right here. Okay. The boundedness theorem states that I can find the upper bound and lower bound of this list right here. Okay, I mean we have positive and negative, right? If you write this number in order, right? Negative first and then positive, from the lowest to the biggest number, right? And they say that according to the boundedness theorem, it said that if 2/3 is the upper bound zero, okay, then all the value that's greater than 2/3 here, it can be zero anymore. It must be smaller than 2/3 in order to be a zero of polynomial. Okay, everybody clear? So the boundedness theorem, it tells you the upper bound and the lower bound. Everything inside the upper bound and the lower bound is zero. It's possible. Okay, it must be inside. If it's outside, we guarantee, according to boundedness theorem, we guarantee it's not zero of polynomial function. All right. So how it goes? It's like this. If we divide px by x minus b, with b greater than 0, and the last row of syntactic division is positive, then b is upper bound. It means that anything greater than b, it won't be 0 for sure. Okay. All right. Now, if we divide px by x minus a, and a x minus a and a less than 0, and the last row is alternatively changing sign, then a is lower bound. It means what? It means any value, any possible 0 you find from rational 0 theorem that's greater, that's smaller than a, so but not greater, that is smaller than a, then we guarantee that those are not 0. Okay, but however, the boundedness theorem, it won't tell you that anything between upper bound and lower bound guarantee that they are 0. No, they just restrict. They restrict the boundary for you so that you can find the 0 easier. Okay, all right. I can give you an example. All right, let me find an example here. It's very easy to get mistake, but I mean, it's not really that bad. Don't worry. Don't worry. Okay. Show that all real 0 x to the 4 minus 3x up x to the 4 minus x squared plus 2x minus 5 lie between -3 and 2. Okay, if we apply the rational number of 0, what do you see? You set up the ratio, right? Phi and phi over 1, right? And you see the factor of phi is phi, the factor of 1 is phi is also 1, the factor of 1 is 1. So the possible 1 is just positive 1 or positive or negative phi. That's the possible number of 0. Okay. And over here, we want to show that all the real 0 between -phi and -3 and 2 only. -3 and 2 only. We should look at, if we can show that between -3 and 2, we don't have to check syntactic division for phi, right? Because look at that. So over here -3, over here -1, over here 1, over here 5. It is between -3 and 2, 2 here. In between -3 and 2 only. Then what is the point of checking phi? Because if we have not learned about this theorem, we just go ahead and check the syntactic division for phi, right? We see if it's turned out to be the remainder turned out to be 0, we know that phi is 0 of the polynomial function. But the boundedness theorem tells you that, oh, if we can show that between -3 and 2, then we don't see the point of doing phi, right? Doing phi. No, we don't have to. All right. All right. So how we're going to check it? Maybe between -3 and 2. All right, that's easily over here. So you see b value is the greater than. So let me check with this one first. So to do syntax again, we have to do syntactic division for 2. So up and down 1, 2, -1, -2, 0, 0, -5. Okay, and we gotta see is the sign changing or not, because if if the last row, it's not the sign change. If the last row of syntactic division is positive, I don't see that I missed anything. Oh, I think I missed something. Again, you see, I only missed. So because we're missing, sorry, I haven't put in order yet. So this is 2 divided. So 4 degree, right? This is 4 degrees. So 1, so third degree is 0. I'm sorry. So the second degree negative. So I missed the coefficient. And -2 and -4. So we don't know. We spend too much time over there. I try to go fast and see that you try to go fast. Very easy to get this stuff. So let's slow down a little bit. So drop that 1 down. So you have 2, 2, 4, 1, right? 2. Okay. So this positive. See, 4, 8. You go. They say what? Because b is greater than 0. So b is 2. All the last row syntactic division is positive. All the last row in syntactic division is positive. Look at that. All the last row of syntactic division is positive. It's all positive. Then 2 is upper. Okay, then 2 is upper. All right. Now, for the value less than negative, less than 0 is negative. So a less than 0. So we will do division again. -3, 1, 0, -3, 2, 5. So 1, -3, right? -3, 9, 6, -18, -16, 48, right? And 43. So I know that this is different from 0. So I know that -3 cannot be factored and extended because according to rational zero theorem, -3 is not a possible 0. So we know -3 is not, but we know that the last row of this syntactic is sign changing all the time. And if the sign changes all the time, we know -3 is lower. Okay, and if 2 is upper bound and -3 is a lower bound, then we guarantee we know possible 0 must be between -3 and 2. It must be between -3 and 2, and you have to use parentheses because we know that 2 and -3 is not 0 because the remainder is not. Okay, we just know that between -3 and 2. So look like it must be 1 or -1. It cannot be 5. Okay, it must be 1 or -1. Do you see that? But we don't know which one. 1 or -1, we don't know. So the boundariness theorem, it just restricts the boundary, but it does not guarantee that every possible 0 inside that boundary is 0. No. Okay, we have to keep doing more division to check. All right. So I think that's all for the boundariness theorem. Is the last concept we'll learn in this section. We have to practice it when we have to practice. So many theorem today. We talk about Cauchy, we talk about Decartes, we talk about Gauss. They all related to each other. When you go through all the theorem with me, some of you find it hard to relate all of them, but actually they all related to each other. Okay. Please watch the video again if you have not understand anything. Okay. If you have not understood the concept here after watching the video, then please just send me a campus message. I'll try to explain one more time to you guys. All right. I'll see you next time in the next section of 4.4. Bye bye.